Okay, we are going to just discuss a little more about ionic compounds. Okay, so ionic compounds. Well, these are compounds that form between a metal and a non-metal ion. Okay, and in fact, the ionization process happens during the reaction between metals and nonmetals. And so we're just going to kind of do an overview of this. One example that we did the other day was reacting magnesium plus oxygen, okay, to get magnesium oxide. We'll go through how this naming works a little bit later on. I just want to make sure everyone understands how this happens, okay? So again, just to review, you get your Lewis dot diagrams, which are just showing your valence shell electrons, and everything on the inner shells is in complete or full shells, and so is not involved in the reaction. So when you put these near each other and you provide a little bit of a spark to get them going, magnesium's electrons will migrate on over to oxygen. And what you'll end up with is an ion with 2 charges, positive, and an ion with 2 charges, negative. Why is that? Because we're taking electrons away. We're removing negative charge, right? It's like subtracting a negative number. You get more positive when you do that, all right? And here we're adding negatives onto oxygen and therefore turning it more negative. Remember, every one of these dots represents a negative charge, okay? And then what ends up happening is these are electrostatically attracted to one another. So just like, you know, a balloon that you've rubbed on your head and given a static charge to, opposite charges attract, and these two ionic, you know, atoms, I guess, or ions, will associate with each other and link together due to their opposite charge. Now, when we talk about an ionic compound here, and we'll use this as our example, but it could be any. Actually, we won't use this as an example. Let's do another one. Let's do table salt. So table salt is when you have reacted sodium and chlorine. Now, if you did this reaction directly, like if you took chlorine gas and you took sodium and you put them, you know, together, you'd get a pretty outrageous reaction. You wouldn't really want to be anywhere near this. It would be highly energetic. These are two very reactive chemicals, right? So sodium is one of the most reactive metals, and chlorine is one of the most reactive nonmetals. So what will happen, right, is sodium, being the metal, will lose its electron, ending up being a positive ion, and chlorine will be negative. And you end up with this, NaCl. Now, in real life, what are these compounds going to be like? Well, if you think of table salt, what can you say about it? And all ionic, and you know, this kind of like stretches for most ionic compounds. So the ionic compounds that we've seen so far are magnesium oxide and sodium chloride, but there's many more out there in the world, and we'll start looking as we go. But it's interesting to start noting what kind of properties they have. So when you think of table salt, right, what do you think of? What is it like? So, you know, table salt is crystalline, all right? So one thing is that ionic compounds are crystals. Some are very obviously crystals, like table salt is. Others, it's less clear, like magnesium oxide looks like a white powder. Magnified, you'd see that it has a bit of a crystalline structure to it. So they're crystals. I'm going to give you a few more here, because maybe you don't know this, but 2 is they have a high melting point. If you've ever tried to melt salt, it's pretty tough to do it. Sugar, on the other hand, which is also a crystal, but it is not ionic, it's a different kind of crystal, melts at a relatively low temperature, right? You can do it right on your stove. It's pretty hard to melt salt on your stove. So high melting point. 3 is they dissolve in water. They tend to dissolve in water, and we'll get into the why that is a little bit later as well. So how do you spell dissolvers, or 2 S's? And the 4th thing is they are electrolytes. I'm sure you've heard that word before, like, you know, Gatorade is full of electrolytes, or your favorite sports, insert favorite sports drink here is full of electrolytes. Disclaimer, I'm not sponsored by Gatorade, but if they'd like to sponsor me, I will always use their drink as an example in my videos. Okay? Just kidding. Okay, so anyway, electrolytes. Does anyone know what an electrolyte is? So we just saw this little kind of short demonstration, and what I did was I took deionized water, so water that's essentially completely pure, distilled water if you want, water with only water, pure water, and we took a battery, a 9-volt, okay, and we took a little light, an LED light, okay, and we attached that little light. Here it was green. Okay, we attached that little light like this, and like this, to one terminal, to the correct terminal, and like this. And we noticed when we had it set up with pure water, nothing happened. But then I dumped in just some standard table salt, which is sodium chloride. Just added it into this water, and after a few seconds, all of a sudden the light got brighter and brighter until it was glowing just as brightly as it was when we connected it directly to the battery. So what's going on there is this NaCl, this ionic compound, is acting as an electrolyte. And so you might be asking, well, how is it doing that? So there's two things kind of acting together. First, the dissolving of NaCl, and then its behavior as an electrolyte. So why do ionic compounds dissolve? So before we can look at that, we need to look at the whole idea of them, okay? First, crystals. Why are they crystals? So this is called actually, what is it called? I think it's called like a unit formula, I think is the name of it. Formula unit, sorry. It's called a formula unit. My bad. And it does not imply that NaCl is a molecule, because it's not. It is not a molecule. A molecule is its own little bit. We'll talk about molecules later. So anyway, what ends up happening is if we have chloride ions, right, which are negative, so we'll do them in green, chloride ions, and we have sodium ions, we'll do them in orange, which are positive, and you have a lot of them, like you would in any reaction, you'd have a whole lot of them. They end up forming this kind of like matrix with each other, okay? So in other words, these ions are attracted to one another in such a way that they start to build up from very, very small to very, very large in a very regular pattern, okay? So you can imagine if this goes on for, you know, billions and billions of times, that you're going to get a pretty regular shape building up. I'll just grab a picture of a salt crystal, and you can kind of, I think, get an understanding of why these things form such regular crystals. So what ends up happening here, okay, so we start with these ions, these tiny little ions, and they build, right? They build up and build up and build up, and they build up in 3 dimensions. So this would go back, right, in this direction, and you'd end up like forming, if you do this enough times, cubes, right? So this is a 1-to-1 crystal, and really most ionic compounds that form a 1-to-1 relationship end up with square crystals. So we're just looking at a video about guys finding salt cubes on the shore of the Dead Sea, the saltiest sea in the world, and you know that's kind of why that happens. Okay, so that's why they're crystals. Why are the melting points fairly high? Well, the melting points are high because in order to melt this, you have to add enough heat that these attractive bonds between the negative and positive ions start to break, right? And it flows around. And you could do that. You just have to get it like extremely hot. So for table salt, it melts at 801 degrees Celsius. And that's much higher than, say, something like sugar or other candy, all right? And the reason why, again, is because you're having to break apart these relatively strong bonds. They're not as strong as molecular bonds, but they're pretty strong. So why do they dissolve in water, and why are they electrolytes? So we gotta jump slightly ahead here and look at a water molecule. So a water molecule consists of oxygen and 2 hydrogens. And it turns out that oxygen has this property called electronegativity, which just means it attracts electrons to it very strongly. And so these are not ionic bonds. These are molecular bonds. They're different. They're sharing electrons here. But those electrons spend their time close to the water molecule. What that does is it gives the water molecule a slightly negative end and a slightly, essentially double positive end, really. Okay? And so you can imagine now that in your cup of water, you have billions and billions of these floating around, and then you introduce to it some salt crystals, right? So your negatives and your positives come in here as salt crystals, and water, because it has this like polarity to it, it's called polarity if it's got two sides, it's attracted to the negative and positive and ends up essentially pulling this all apart, okay? So it pulls your crystal all apart from its regular substance, it pulls it apart. And what will happen is something like this. So you can imagine the negative ion on there will have an attraction for the positive side of water. So what you'll get is you'll get the surrounding of the crystal by water molecules, right? Because those positively charged hydrogens will attract over, and water will literally surround. So now this ion, right, has a bunch of water molecules around it. Well, to all the other water molecules, it just looks like the outside of a water molecule. Do you get it? And then the positive ones, right, they get surrounded like so, right? Because the negative of the oxygen is then attached to them, okay? But when you think about it, what we've created here are these like little structures all through our water that overall have a negative and a positive charge, okay? So that's why they're dissolving, right? The water's attracting to them and splitting them apart and floating away these ions out into the rest of the water, okay? But that also turns the water that happened to into an electrolyte. So if we can imagine here, here's our beaker, okay? Here's our beaker. And we put two probes in there, two, like an anode and a cathode, basically. And we put a voltage across, okay? Well, these things, these structures, are going to start to attract. So I got a positive side, I got a negative side. We don't really talk directly about how this happens physically, but this is what's going on. We would say that the negative, oops, I don't like that color. We would say that the negative dissolved ions are going to start traveling here, right? And that the positive dissolved ions are going to start traveling over to here. They're attracted to this voltage, okay? If instead of having it like that, where we were just letting charge flow, we make it into a circuit like this, and say put a light bulb on here. Okay, there's our light bulb. This will start to glow as soon as we add that salt and allow this current to start flowing. So it's actually the ions themselves being attracted that is completing this circuit and allowing the glowing. Okay. So to sum up, ionic compounds are a reaction or formed by a reaction between, I guess that's fine, metal and non-metal. Okay? Metals always lose electrons to form positive ions, right? And non-metals gain electrons to form negative ions. Okay? And the last thing I'm going to state here is ratios are such that there is no net charge on the ionic crystals. So I just want to do a few examples of this. So here's aluminum, right? We know aluminum looks like this. We know aluminum will form a 3+ charge. Let's say someone asks you, what will aluminum plus oxygen make? And you would say, well, let me just think about that. So we got 6 there. We know that it's going to gain 2 to form a 2 negative, right? Before we were drawing arrows, and that's a proper full Lewis structure. But if you look here, you can probably come up with what the proper ratio is going to be. And if you think about it, 3 and 2, well, the lowest common multiple of those is 6. So in other words, we're going to need 6 total positives and 6 total negatives. So we'll get 2 aluminums, right? There's 2 of those, and we'll get 3 of these. And we'll have to form that compound in this ratio. 2 aluminums for every 3 oxygens keeps that charged, the charges balanced, right? So the 2 aluminums here give you 6 total positive charges, and the 3 oxygens here give you 6 total negative charges, and 6 plus -6 equals 0. Okay, so let's try another one. So magnesium. What ion does it form? So magnesium's in group 2. We don't really even need to draw the Lewis structure to know that it's always going to form a 2+ ion. Okay, and let's say that you're reacting it with chlorine. Well, chlorine is group 7, so it's always going to have 7 in its outer shell. It gains 1, right, to get to 8. So it's always going to form a negative. Well, this one's pretty easy. We're going to go Mg. That's got a 2, but we're going to need 2 chlorines to even out with it. Okay. Let's try one more. How about beryllium and nitrogen? Well, beryllium, that gets a 2+. Nitrogen gets a, how many minus? A 3-, and that's just looking directly from the periodic table. You can sort that out. Okay, nitrogen has 5 electrons in its outer shell, so it needs 3 more to get to 8. So in this case, we're going to need 3 of these. We're going to need 2 nitrogens. Okay, why? Because we need +6 and we need -6. It's the lowest common multiple. The lowest common multiple of 2 and 1 is just 2, and so on, etc. So really, you could make from the periodic table, you could figure out what the ratios are of any ionic compounds. Okay, and that's what we just do. We just draw the formula unit, but we realize that these are actually like forming gigantic crystals with billions and billions of these ions all mixed together. And most ionic compounds follow these rules. Every once in a while, an ionic compound will not dissolve, but that's fairly rare.